In this video, we'll be looking at the Arduino Nicla Sense ME. It's a small, well, this is actually the finished product. It's a small, well, testing, 1, 2, 3. It's a small microprocessor with tons of capability, so stick around. Alright, so today we're talking about IoT, so specifically the Internet of Things. It's a huge umbrella that's all about small interconnected devices that extend a digital reach into our environments, if that means anything to you. What it really means is when we look at microcontrollers, and microcontrollers are circuit boards and mini computers or programmable logic controllers that you can add to your projects or in your environment that can provide capabilities. They make smart devices, basically. And when you think about smart devices and microcontrollers, Arduino has to be part of the picture. They've been around forever. They're the easiest turnkey devices that you can get your hands on, low cost, big capability. You can extend them however you need to do just about anything. And when we look at those like the Arduino Uno, the Mega 2560, there's lots of variations. The Nano RP2040, it's got a different processor on there. The Maker Zero, the Nano 33 BLE, lots of variations. And all they really are just combinations of additional chips paired up with the Arduino chips in a lot of cases. If you work with an Arduino, they're easy to get started and you can add just about anything because they have these headers, basically they're GPIO. General purpose input output, so you can connect other modules and other capabilities, and usually you use a bunch of breadboards and wires to make it all work. And you might be able to do just about anything you want with them, but it might have a larger form factor than you'd like. If you need something more capable and more industrialized, then Arduino is now offering Pro series, where you can look at the Portenta H7, the Nicla Sense ME, the machine control. These are all heavy-duty industrial devices that have more capability, higher processing speeds, more RAM, more resources, and more capabilities. Today we're looking at the Nicla Sense ME. It's a small form factor about the size of a postage stamp that's got tons of sensors on there for IoT purposes. And when I think of IoT, or when I mention IoT, I mean it's got BLE for wireless connectivity, so you can talk to it from your phone or other devices that support BLE. And it's got lots of sensors that can tell you about the environment, like IMU or an inertia measurement unit, barometric pressure, air quality, accelerometer, compass. There's lots of capabilities to this little guy. So we're going to jump over and look at the data sheet for it, and that'll tell us all the specific capabilities, and then how we can apply it to our environment, to a new project, to add a digital capability to make smart projects. All right, for that, let's head over to the computer. All right, over at the Arduino website, the Nicla Sense ME's elevator pitch is that it houses 4 low-power sensors in a small footprint, enabling powerful data fusion capabilities on the edge. Analyze motion and environment with industrial-grade Bosch sensors that can accurately measure rotation, acceleration, pressure, humidity, temperature, air quality, and CO2 levels. If that's not enough, this thing's only the size of a postage stamp. It's a little bit smaller than a quarter, I would say. All right, before we dive over into this data sheet, let's look at the sensors that are part of this board. We've obviously got the Nicla small form factor. It's the smallest form factor yet for any Arduino boards with this amount of capability. They have a BHI260AP, which is an AI smart sensor hub with integrated 6-axis IMU. So 3-axis accelerometer and 3-axis gyroscope for activity detection. It's got this AI smart sensor hub which can interpret movements and determine what you're doing, if you're riding a bike or you're swimming or you're doing jump rope or things of that nature. It's really pretty cool. It's powered by a 32-bit Synopsys DesignWare Arc EM4 CPU. It's got the data sheet there if you want to know all the gory details about it. Next we have the BMP390, which is the high-performance barometric pressure sensing module between 300 and 1250 hectopascals with low drift. But that's going to give you altimeter. You'll be able to calculate the pressure into your altitude and vice versa. It could be useful for something like a quadcopter that you want to maintain a specific altitude during flight or something of that nature. You can also determine when weather systems are coming or when rain can be expected. Data sheet for that's also there. BMM 150, which is the magnetometer, which has it's a 3-axis magnetometer. It has an X, Y, and Z axis, which is helpful if you're using magnetic encoders, or if you just need to know the orientation of the device, or in this case of the sensor board. The BME 688, which is the environmental sensor, which can measure pressure, humidity, temperature, onboard smart gas sensor. It helps in determining air quality index. It'll also let you know about VOCs and CO2 emissions. So if you have an environment or your application where you need to know what the air quality is like in the general vicinity of the sensor, then this is another module that you can leverage. And it's kind of amazing that they could put all of that into this small board. The tech specs at a glance, we've got the Cortex M4 NRF 52832 microcontroller, and that's running at, I believe, 64 megahertz processor speed. It's got a micro USB connector on there. It's got a built-in RGB LED, which is accessible over I2C, which is the communication protocol. In terms of digital I/O pins on the board, there's 10. 2 are shared with I2C and 4 are shared with SPI. Those are 2 different communication protocols that you can connect other devices and components with. So with those 10 digital I/Os, you could connect to switches or lights or buzzers or anything you need to control or sense, and that makes it easy to integrate with. Analog input pins, those are going to give you a voltage, resistance, or impedance across 2 pins or a single pin, and that's useful for analog components that you want to integrate with. There's plenty of analog devices out there and modules, and having 2 pins is nice for that. You can also do like pulse width modulation on LEDs or something of that nature. 12 external interrupts. Connectivity, they've got the Bluetooth module, which is nice. Doesn't have Wi-Fi, so you'll have to relay that through a proxy, either a cell phone or another device that's listening and communicating with this device. So that's your best bet. Does have UART. You can connect with serial and debug information when you're working through your code logic and all that fun stuff. I2C, it's got, I believe it's got 2 actually, as well as SPI, but only 1 is exposed to the pin headers. I2C and SPI allow you to connect a monitor or other I2C device or module, like an OLED display or something of that nature. The operating voltage is 1.8 volt translated to 3.3 on the external pins, which makes those pin headers compatible with other microcontrollers. Board power supply, 5 volt coming in from your USB or voltage in. It also supports the lithium-ion LiPo single cell at 3.7 volts. But the battery connector is a low-profile 3-pin JST 1.2 millimeter pitch. This thing is tiny and flat and hard to find. The tools to even make these connectors are expensive. I haven't been able to locate a single-cell LiPo with this pin already installed. I suspect that that'll be coming to market as these devices get more prevalent out there. Current per pin, 4.7 milliamps. Not much, but enough to control your logic and GPIO. Like I said before, the 64 megahertz processor, not a beast, but it'll get the job done. Memory, what do we have? 64 kilobytes static RAM, 512 kilobytes flash. The thing that's nice about Arduino that everyone loves is when you upload your sketches, they're compiled and uploaded to the device. You don't lose them when you disconnect the power. So it's permanent. It's not a heavy OS. It basically just has a bootloader that initializes the microprocessor or microcontroller, and then it executes your logic that's compiled from your sketch. It's not prone to error or corruption, so that's really nice. Having 512K flash is good enough for the size chip that this is. 2 megabytes of data logging and 2 megabytes of storage. The weight's 2 grams, and yeah, it's under an inch, 22.86 by 22.86 square. So in addition to those general specs, there's a data sheet that you can dive into and get all of the details about the individual sensors, what their accuracy, tolerances, and stability are for the pressure, for the magnetometer, the artificial AI operating gas sensor, and the microcontroller specifically. So if you need that level of details, you need a pinout or a block diagram of the design of the system, then that's where you want to go, to that data sheet. I'll put links in the description to help you out. I'm not going to run through this right now. There's a lot information that's overkill for this particular video. The intent of this video is really to just walk you through and give you initial exposure to this sensor and allow you to start thinking about the opportunities and how you can integrate it. To continue with that, there's a quick start guide. This quick start guide is very useful in getting you set up and running with it, installing the board profiles and all necessary resources to support and compile your sketches for the board. Also additional suggested libraries, Arduino BLE if you want to communicate from the board, and some additional examples. So this board uses Embed OS as an hardware abstraction layer, if you will, to the microcontroller and the individual components. And the support for that isn't broadly available for a lot of libraries. Many of them will immediately be compatible, but the few specific related to communication, dealing with processors, and the BLE can be found here under this tutorial section. With that, we're going to put this thing to use. And I've got an idea for how we could use it in the shop here in my makerspace. And for that, let's go back to the table. All right, so the idea that I have is to use this Nicla Sense, which is an IoT device on steroids. With all of those sensors and all of those capabilities, it would be interesting to see how many devices I could use this for to make it a smart device. And what I mean by that is I've got a 3D printer in an enclosure. That enclosure is important to when I'm 3D printing in that environment, what the humidity is, what the temperature of that environment is, if there's any anomalies or VOCs or the air quality changes, then it'd be interesting to know. I might need to turn on ventilation or turn on a fan or a light or something of that nature. And this sensor has all of those capabilities, which would be easy enough to plug in that environment and then just look at a dashboard that tells me when things look wonky, then it's time to go check out that machine. Maybe sends you a text message or something of that nature. In addition to the 3D printing, obviously the laser is a machine that can produce a lot of bad air and needs to have an exhaust fan, and having a sensor on that would help you understand, when those conditions change. Maybe you don't need to babysit them as much as you normally would if you have a sensor like this monitoring it for you. CNC, if this is mounted to the frame, it could tell you the vibrations and changes in behavior that may indicate that maybe your machine's due for some service. Maybe you need to check out your linear rails or your ball screws because there's vibration that's occurring that shouldn't be happening or isn't normal for the machine. So these are all opportunities to make these machines more intelligent. Generally, the computational capabilities of each of these machines is just limited to their core responsibility, and that's moving a print head around or moving a spindle around or moving a laser around, but beyond that, they're not very smart. So my thought is that we could just use this simple sensor as the Nicla Sense ME exactly as it is with a small form factor. We just create an enclosure and put a display on front that gives us some immediate feedback to those sensors and those parameters that matter the most, like VOCs, gases, temperature, humidity, and vibrations. These are all important to all of the machines in my shop. So in today's video, we're going to take this over to the desk. We're going to work in the Arduino environment. We're going to write a script that allows us to read all those sensor values and then to share them out over the BLE channel. The BLE communication will then allow for us to design a central BLE receiver that can listen for all of these sensors and aggregate it all into one dashboard. That dashboard will allow me to turn my shop into an intelligent smart shop filled with smart machines that can all tell me the varying climates and environment conditions of each of the machines at a simple dashboard. That's a little ambitious for this video. Today we're just going to make the small Nicla Sense sketch that provides that capability, reads the sensors, and sends it out over BLE. And then in future videos, if you guys want to see the follow-up, then we can develop that dashboard and we can develop that controller that can listen for all those sensors and devices. Now these things aren't cheap. They come in around 70 to 90 bucks, just depending on where you get it. So this is an investment on each of those machines. And so to protect it, put it in the right form factor, give it a display, and make it a finished product, it's going to take a little bit of work. But let's go over to the computer and get to it. All right. Over in Fusion 360, I designed a footprint for the Nicla Sense ME. Basically just wanted to capture the exact location and profile of the board where the header pins are and where specifically the micro USB connector is. And then with that, I designed an enclosure around it. I brought in the OLED display and oriented it. This is a 0.94 OLED display. Oriented around it using a couple sketches, then added in some 3mm screen, which is totally overkill. And then I created an enclosure around that screen from wood. Originally designed this to be from aluminum, but it really doesn't matter. This is just a prototype, and wanted to make sure that I had all of the orientation and the location of those things in place. Once that was complete, I can get rid of this. I started to build a riser, and that riser, the intent of that is to really protect the board so that it doesn't ground out on any enclosure, should the enclosure be made from, metallic ferrous metal. So that protects it from grounding out or any pins making contact, and it fills in the remaining space, as well as allows a air chamber for the gas to be observed. Alright, with that, let's bring the case back alive, and we'll see that we have that nice black out interface that I love so much. We can hide the screen. You can see the OLED in there. All of the remaining space is filled by the 3mm plexi, as well as some air holes for breathing on the bottom. Now, the next step was to mill this from wood, and to do that, had to step over into the manufacturer environment. In the manufacturer environment, I set up the stock size, which would be a block of wood. First we do a face, then we do a 2D adaptive pocket, contour to clean it up, bore out those air holes at the bottom, and then an external contour with tabs at the bottom so that it didn't break free. Exported all these operations and ran them on the EVO 1 CNC from a piece of scrap laminated wood. With the enclosure complete, it was just a matter of assembling it quickly and painlessly using the 3D printed component, riser, and the enclosure and the laser cut acrylic. Before we get too far, electronic projects always start with good circuit designs, and for that I rely on Altium Designer. From simple to complex, if you haven't taken a chance to download a free copy and see what you're missing, I've put links in the description, and with Altium Designer, creating these complex projects is a piece of cake. Through your development, you'll be empowered to do your best work as you grow into its more advanced capabilities. The link in the description below will allow you a free trial version of the software so that you can check it out and see what enterprise class ECAD feels like. Now back to the overview. Alright, so to make all of this happen, we need to write a sketch, and that's ultimately the firmware and logic that we'll upload to the device in order to perform the tasks that we want it to do. And to do that, I'm going to leverage, you could write it all from scratch if I want to integrate at a low level, API level with BLE device, with the Bosch sensors, with the OLED screen and all of that fun stuff, but there are plenty of libraries out there. And in the Arduino environment, in this case I'm just using 1.8.16, you can go to Manage Libraries, and that generally will let you run some searches and find out what's available that you can repurpose and apply in your sketch to save you a lot of time and complexity. BLE, for example. You can see that there's several BLE. Generally, in this case, I'm going to go for the ones that are made by Arduino. They're going to generally be the most stable and mature libraries. Arduino BLE is one that I used in this, as well as the BHY2. This is by Arduino. It's a library for the Nicla Sense ME. So once I install all the necessary libraries, those are included in the sketch here. You see there's a Nicla system library. This provides low-level access to basic resources on the Nicla board itself, like the LED, RGB LED. Arduino BLE is a library that's going to allow us to communicate over BLE. And to do that, we need to basically register an identity and some characteristics that are part of that service or identity. And then the BLE library will advertise that out so other devices can connect and consume those services and characteristics. Arduino H provides some core capability. The Arduino BHY2 library is what communicates and manages the Bosch sensors on the Nicla Sense ME. The U8G2 library is what will interact with an OLED device or OLED display. In this case, I'm going to use a 0.94-inch OLED display to finish up this project to make it be able to present my logo and some attributes about the air quality, the temperature, humidity, all of the basics, so that you can see what it's detecting at a glance, but it's also transmitting it over BLE where it can be aggregated into a dashboard. So we've got a couple libraries for that, and then we've got Wire. Wire allows us to communicate over SPI. So with that, we need to instantiate a few variables that'll be used in this sketch. For me, I'm going to look at the temperature, barometric pressure, humidity, gas, magnetometer, the gravitational orientation of the device, and some motion. And this is the AI motion, so you can read the accelerometer and motion sensors in the 9-axis IMU. In addition to that, we also configure the OLED display, and this is a simple OLED display, 0.94-inch. You can get on Amazon, and this will communicate directly with it and simplify that process. Now, once I'm reading all of those sensors, I'm going to have to define the characteristics for those. And to do that, initially we're going to have a service, and this is basically the identity of the device. In this case, it's the ShopSense service. And this is the unique identifier that all of my peripherals will have. And therefore, if somebody's looking for one of my ShopSense peripherals, they can just look for this ID. They'll all share that as a common identifier. Once they connect to that specific ID, then there's a bunch of characteristics, and the characteristic is like an attribute or an advertised attribute that a service is providing. That's an easy way to think of it. So we've got the temp characteristic, barometric pressure characteristic, humidity, gas characteristic, magnetometer characteristic, gravity characteristic, and motion characteristic. These are all using the same global unique identity with the last digit changed. Now, ideally, you should have unique GUIDs for each of these. I'm just incrementing this last value for each of my characteristics so they all have unique identities. And this is just in the context of this prototype. This will probably change if it goes beyond that. So we've got 201, 202, 203, 204, 205, 206, and 207. Now we've got those characteristics set up. Those are going to be part of the service. We're also going to put the DIY engineering logo in there, so why not include the bytes for that? So this is a chunk of memory that it's going to keep, and if you could visualize that, that's the DIY engineering logo, and we'll see that a little bit later. Next, I'm defining a couple helper methods, and then one of the important parts of any Arduino sketch is the setup method or setup function. This function is called once during initialization. As soon as the processor bootloader has executed and it begins to run your sketch, this is the first piece of code that it runs, and that's intending to set up any conditions that you need set up. In this case, I'm connecting to the serial. We're also initializing the Nicla library. This is a library that manages the Nicla specific resources. And then we're initializing all of the Bosch sensors that we identified above. We're actually configuring them and starting them. There's not a lot to configure them. All of the heavy lifting is done within those libraries, and if you need to know that level of detail, at this point the API is wrapped really well by that, and they only allow you to identify instance and latency, and I haven't really dove into those details, but you certainly can if you need to. For this purpose, we're just instantiating them, giving them basic configuration to identify instance and latency, and then we're initializing them, telling them to start up. Next, we start up the BLE local service. We're setting the local name. That's basically the name that will be advertised for the service that this device is offering to the world. This is called the ShopSense peripheral. We're setting that up in association to the BLE library, and then we're adding all those characteristics. These are all of the attributes or telemetry or metadata, whatever you want to call it, that you want to serve up through that service. So this device is going to be called the ShopSense peripheral. It's going to offer all those characteristics as values that once you're connected to this device, I'll provide for you. Finally, you add that service. The service has been configured with all its characteristics, and it's just a matter of giving it to the library and saying it's time to advertise. And by telling BLE to advertise, you're essentially telling it to start advertise like a Wi-Fi access point would advertise its SSID. Same thing, but we're just advertising a service that has characteristics that can be consumed. Next, we initialize a couple libraries for the OLED display, which are the Wire Begin and the U8G2 Begin. And these are libraries that will manage drawing of the graphics and refreshing of the screen and all that fun stuff. And with that, this ShopSense peripheral is completed its initialization. So this function only runs once. I use function and method interchangeably often, but this function runs once. And then I have defined a few helper functions that will provide values for those characteristics. So just because I've defined the characteristics doesn't mean that their values are updated. It's my responsibility to do that. And to do that, I've got this helper function that can load those sensor values. So when I do that, I just write a value, and then using the sensor service, I can just retrieve the value attribute of that object and write it directly to the characteristic. When I write it to that characteristic, then it's available for anybody that's listening or connected to my service to consume. So I do that for each of the temperature, barometer, humidity, gas, magnetometer, gravity, and motion. Updates all of those characteristics values. And then finally, I check to see if anybody's connected to listen to my service. And if they are, then I just return true. And that helps me to understand for further processing, whether or not I need to update the values. If nobody's listening, does it matter if I update these? So that flag is useful for me a little bit later in this function that's called loop. Now loop is a function that iterates till the end of time, till the microcontroller loses power. This loop function will run, and it'll run through, and when it completes, it will start again. And so this is the most important part of the sketch because it's responsible for doing all the fun stuff. First part of the loop is to get a timestamp of when it started and to also identify a flag. This flag is going to be used later in this to blink a LED. And for me, that's visual feedback if it's behaving the correct way. And I use that LED for a couple purposes we'll see down below. DHY2 update is just to tell the Bosch library to do whatever it needs to do to pull, to process the connections that it currently has with the sensors. So this runs on every loop cycle. It gives those sensors and that library the opportunity to manage all of the connections to those sensors. Next, we update the screen, and to do that, we first clear the buffer, set a font, draw some text, a line, some more text, and then I take the values that have been read and I write them on the screen, and then I draw my logo, DIY Engineering logo, draw X bump, 64 by 64 at a specific location of 70,0. This particular display is 128 by 64, so the 64 pixel height is as high as the display is, and 70 means it's off the center, so it's to the far right of the display. And then we send the buffer. By sending the buffer, it tells the display to update and refresh. Next, if this loop has been running, this loop's a lot faster than you think, so it'll be a few milliseconds. If it's running, and that time that it's been running is longer than 1 second, that could be 100 or 200 cycles. You don't want to, in this case, this logic should only be performed once every second. And that's because it's about toggling and flashing the LED that's on the board. If you don't throttle the LED processing with some logic like this, then chances are you'll never see it blink because it's blinking so fast. So in this case, we want a 1 second blink. And so my update time was the timestamp that we collected when it first started, and the millisecond is the current time in milliseconds. So if it's been more than a second, then I want to toggle my RGB light. So when a second has passed, I'll load the sensor values using that helper method that we already went through. Then I start looking at the flag. So how do I update the LED? Was somebody connected? Then I'll set it to green. If it's toggled and somebody was connected, then I'll set it to red. But if nobody was connected, I'll set it to blue. And so what that logic does, and then I'll flip the flag down here, flag equals 1 minus flag. So what that's going to do is basically when the flag is equal to 1, it's going to be green. When it's equal to 0, it's going to be red or blue. And so that's dependent on whether or not somebody was listening or nobody was connected. And so what will happen on a 1 second interval, it'll flash green, red, green, red, green, red if somebody's connected. And if nobody's connected, it flashes green, blue, green, blue, green, blue, and continuously. And then if somebody connects, then it goes to red and vice versa. So you understand that. That's helpful for when I'm looking at the board, when I'm not physically connected, I can tell if something is connected and listening. And that tells me whether or not the logic is behaving correctly, in addition to the results that are being displayed on the screen. So that's really all there is to it in a nutshell, to read those, what, 5 or 6, 1, 2, 3, 4, 5, 6, 7 different sensors from that board, just using these 7 different variables and objects that interact and read the parameters, and then we advertise those through the characteristics on our service. That's all there is to it. So Arduino makes it really easy. Of course, you could do this in other sensors. You could construct this all yourself on a breadboard, or you can design your own circuit board using Altium. Now, because I'm using all of these libraries, it does make the compile time in the Arduino IDE exponentially longer, which is kind of a pain, and there are a few different alternatives. Maybe we'll go into that in another video, but for now, next thing we need to do is compile the sketch and upload it to the device. And to do that, we need to do a few things in the IDE. First of which is to select the board type, Nicla Sense ME. Next is to identify the COM port. With that, we compile and upload the sketch to the board. Now this takes some time. It'll compile all of the libraries and the sketch itself. This progress bar moves to the right as it completes, and then you'll see more information and a progress status on the serial port down here as that process occurs. Once that's complete, we'll see the board boot up, and as it boots up, you can see the text that we had generated on there where it says shop sense, has the temperature in Celsius next to it, humidity in percentage next to it, and the gas percentage and air quality index next to it. To the right hand side, you see the DIY Engineering logo, which looks nice. And the beautiful enclosure that we made earlier on from some scrap wood provides an enclosure for it to be protected in the environments that I plan to mount this. So hopefully you enjoyed this look at the Arduino Nicla Sense ME microcontroller. It's one of their Pro Series boards. It's got one of the smallest form factors and the biggest capability that I've seen to date. It's easy to use. It's got LiPo capability so that you can run it with a small rechargeable battery and communicate with it over BLE to extend the capability and reach of your products. So with that said, I'll put links in the description below. You can go down there, link over to their website, and check out all of the low-level details about the components that are a part of this board, and some samples and example code that'll allow you to get started quickly using the Nicla Sense ME. So I'm going to get back to programming and extending the capabilities of the ShopSense project. Let me know what you think down in the comments below, and if you have any future ideas, and we'll circle back on this once we get the server component of this up and create a dashboard and all that fun stuff. In the meantime, be safe, have fun, and I'll see you next time.
Hey, if you liked the video, please subscribe to the channel. It's how we're building the community. Also allow me to bring better content. Also check me out on these other social networks. There's lots of cool stuff there too.